is 32 bits. So this means this 2.95 will be written in 32 bits, right? And you know how to write it, yeah? We have the sign, we have the mantissa, and the exponent. So there will be 32 bits. How many memory locations we need? If the size of each memory location is 8.
4 memory location.
Yeah, so this two, if we have this memory and you have this declaration, we will need, the compiler will reserve, based on the type, it will reserve this for X. And the pointer will point here. So this is P. It points to the first one. So the compiler will know, we will have the address. So if this is 0x, let's say 1000. So it will know that it will start from 1000 and it will take 4 memory locations. So all 4 will, or my number will be saved. The X is saved in all 4 memory locations. It's not just in one. So if I have another variable here, char, and I will do C is equal to, for example, and then I use another pointer, char P2 is equal, and I will use it to point to char to C. So this is P2. P2 will be here, not here. Right? P2 needs to be here, not in the second memory location, because second memory location is part of X. And this what the compiler will do. I mean, it will know that it cannot touch those 4, so it needs to go to the next available one, and the next available one is this one. When we declare char C, so this is what will happen when we declare variables. And then P2 will point here. So it's very important to know the type. This is why we said the pointer needs to have the same type as the variable that points to. Yeah, is this clear? I put another example here, again with float and char. This is basically the same example that I showed you, yeah? I have the different names here, but it's the same. So C, pointer C, CPTR is here, not in, assuming that this is 8-bit, yeah? Of course, it's not always 8-bit, so it depends on the size of the memory. But here I'm just explaining the concept. So if it was 16-bit, if this was 16-bit, then FPTR will hold, or the first variable will need 2 memory locations, 16 and 16, 32. And then this will be for char. And for char, we will use just the first 8-bit in one memory location, and the compiler will know this, so it will just take the first 8-bit. And this is how it works. All what you need to do, so you don't have to worry which memory is reserved, which memory address is allocated to the pointer. All what you need to do is just to use the right type, and that's it in your code. Right, style of declaration. We already showed you that this is how we declare a pointer. Of course, we need to use star, but can you leave space or not? I think this is optional. You can, for example, write int integer, for example, star without space and then space, or you can have space in between, and they are all correct. But I think most of people, they use this one, the first one. But they are all correct. You leave space or you don't leave space, it's fine. One very important point here as well is pointer declarations only apply to the first identifier. So if you do this declaration, this one is not a pointer. intptr2 is not a pointer. It's like an integer, normal variable, and it's not a pointer. The first one is a pointer. So you have to apply star to all variables that you want to be a pointer. Or you can have them in separate declarations. This is if you want to have all of them in one declaration. Like for variables, right? We can do an integer x, y, z. Yeah? If I want all of those to be pointers, then I have to do it star x, star y, star z. Those are all pointers. Right, I think that's it for pointers. Again, this is just like an introduction to pointers. We will use them. You will see the benefit of using pointers with arrays and functions. So we will use them again in the next topics. Bit manipulation. Second part of this lecture is about bit manipulation. So as I said, when we have a microcontroller, we connect devices to different devices to microcontroller. Some of them will provide multiple bits, and we do the same when we output as well. Output device, we can have multiple bits as well here. When we read the microcontroller, when we read those ends, usually we have a variable, right, in the microcontroller, variable x, and this variable will hold the values that we receive. This is how we work, right? Like what we did when you want to receive, for example, deep switch values. I can assign them to a variable, and then I can work with my variable. So this is what we usually do. And then, as I said, sometimes we need to check some specific bits. Sometimes we need to change a bit, and then we output the data. It depends on our application. So we need to do some bit manipulation. And in some cases, we call those ports. Input-output ports, buses. Right, so this is what I was explaining. Now, to do bit manipulation, we need to use some operators. And the operators that we use are called bitwise operators, and those will help us to do those operations. Of course, we know if a bit is on, its value is 1, and off, its value is 0. And then based on this, the different operations that we can do is to turn on a single bit, or we use the word set. Setting a bit is like turning it on. So we put the bit to 1, turn off or clear a single bit. We say single bit, or it could be multiple bits, 2, 3 bits at a time. So it's not necessarily just one. Again, it depends on what you want to do. We can toggle as well, a single bit or multiple bits. We can test as well a single bit in a port, and we can perform shift operations as well to change the position of the bits. So to do this, we need to use bitwise operators, and we use the hexadecimal notation. Preferably, we use hexadecimal notation. You can work with decimal, you can work with octal. Binary, as we said, standard C doesn't have binary. You need to call extra libraries to work with binary. But we work usually with hexadecimal, because hexadecimal is the closest to binary, and it's easy for us as a human to, when you write F, it's easy. You know that's this 111, 111, so you can make the clear, quick conversion. So we work with hexadecimal, and of course you can work with decimal. It's up to you. But the best one is hexadecimal, and we use the bitwise operator. So the bitwise operators that we use are the ones that I have in this slide. The first one is the AND, the ampersand or the AND, this one. And there is a difference between using double or just using one, right? Where do we use the first one? This is a logical AND. The one that's the gate, the AND.
Doctor, we
Yes.
use the first one in if conditions.
Yes, good. So the first one, we use it in conditions. We say, for example, if x and y, for example, this will return true or false, right? So the answer here, it will be true or false. So if x is 0 and y is 0, so both of them are 0, so false, 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 and false, it will be false. If they are both 1, then it will be true. The condition will be true. So it will return true or false. But the other one, we don't use it this way. We use it, for example, if I have char x, y, z, I have x is equal 200, I have y is equal 100, and then I can do z is equal x and y. So it's like an arithmetic operation, but this one is a logical operation, logical AND. So what will happen here? When I do, what will be the value of z? I do z is equal x and y. So the operation that happens here is, we know that we will have 8 bits for 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits for x, 8 bits for y, and z is the AND. So we do first bit and first bit. So 0 and 0 is what? If it's 0, then it's 0. If it's 1, 0 is 1. So we use the logical AND, bit by bit. So